No, había cambiado las condiciones de Google y eso, y te dice, por eso
corremos mucho. Le pongan el asiento del lado mío.
Sí.
¿Quieres probar los míos? ¿No tenés YouTube? No te funciona.
No. Anda.
Bueno, para todos y todas es un gusto presentar una vez más a Igal y Szleifer. Creo que la gran mayoría de ustedes ya lo deben conocer, así que voy a ser breve. Igal es profesor de Ingeniería Biomédica y Química en la Universidad de Northwestern. Trabaja en distintos temas relacionados con materiales blandos y biofísica. Uno va a hablar de Martina. Y bueno, quería mencionar, como siempre lo hago, siempre la buena disposición que ha tenido ahí a lo largo de los años tener estudiantes de doctorado y postdoctorado argentinos. Siempre en su grupo de respuesta fue un lugarcito donde uno podía ir a tomar mate a las 4 de la tarde y con argentinos. Y bueno, Igal tiene gran relación con el departamento, de hecho se tocó designado en la cosa de la UBA. Bueno, gracias.
Tuve una CB. Tengo afasia. Tengo dificultad para hablar. Por favor, tengan paciencia. Local volume fraction, packing domains, scaling properties, and electrostatic interactions of chromatics. Marcelo Carignano and Martin Unger worked on the chromatin theory. Richard Knapp and Paola Gonzalez worked on the one nucleosome. Chromatin refers to a mixture of DNA and proteins that form the chromosome found in the cells of humans and other higher organisms. Chromatin has many components. At the smallest scale, chromatin is double-stranded DNA. DNA together with histone octamers, such as proteins, form nucleosomes. Nucleosomes could be thought as bits in a linear polymer model. The polymer holds to form an irregular fiber. Further heterogeneous folding form the nucleosome. Physical genomics. How is chromatin structure and organized? How does chromatin structure change due to external and internal cues? How does chromatin structure influence transcription? In this talk, I will concentrate on the first question on one nucleosome. One nucleosome. Relight. Little relight. We represent the nucleosomes as follows. DNA is represented in sugar phosphates and a nucleic base with histone tails. Tails or no histone tails. We employ a physical model that predicts the effect of the environment, ionic environment, charge and structure of chromatin on the nucleobase scale length, nucleosome length scale. We employed we use the molecular theory previously developed in our group to investigate and predict, among other things, the charges and thermodynamic properties of tether-weak polyelectrons. Chromatin is a polyelectron. This detailed molecular representation of the nucleosomes allows us to include chemical reactions in the theory. We include 21 different different chemical reactions in the theory. The free energy functionals in our model include this. The theory explicitly considers size, shape, charge, conformation, and chemical state of all molecular species. Here we show the result of for one nucleosome without Houston tails. The central figure shows the total effective charge as a function of KCl concentration at pH equals 7.4. With increasing KCl, the charge of nucleosome reduces. The total effect, the total charge is the sum of the DNA phosphates and the charge of the histone octamer proteins. The histones are positively charged since there are more basic amino acids than acidic amino acids. The DNA phosphates are negatively charged. They are larger than the positive charges of the polymer proteins. Thus, the nucleosome has a negative charge. Ion binding of K+ ions to DNA phosphates and acidic amino acids increases with increasing KCl. Also, the charge of the basic amino acids decreases due to Cl- binding. Note that of the 300 phosphates, roughly 200 are charged. Thus, a large number of phosphates are condensate with K+ ions. The effect is that the total negative charge of the nucleosome reduces with increasing KCl concentration. The charge of the nucleosome also influences the behavior of the counter ions. Here we calculated the excess amount of K+ ions that surrounding the nucleosome. The non-zero value of the K+ ion excess indicates that the nucleosome the non-zero value of K+ excess indicates that the nucleosome is surrounding with a counter ion cloud. This double layer string electrostatic interactions. The large number the ion excess indicates that the electrostatic interactions are strong. The amount of ion excess follows the amount of charge of the nucleosome. Here we compute the charge and excess, ion excess for the nucleosome with linked histone tails. The trend is similar, but the values are very different. Here we compare the charge for the nucleosome with and without linked histone tails. Comparison of the value of shows a very large difference in charge. A nucleosome with tails has more lysines and arginines. This extra base results in a less negative charge of the nucleosome. Here we show the total volume fraction of the nucleosome with and without tails. We see darker colors which corresponds to the histone proteins. Yes. We also see the phosphate backbone surrounding the core. Notice also the heterogeneity. Here we show the corresponding electrostatic potential. The magenta or thin colors correspond to negative potentials, that is, phosphates and acidic amino acids. The green color corresponds to positive potentials, that is, basic amino acids. The phosphate backbone is clearly visible. We can also see the histone tails with lysines. Here we define a local pH as negative logarithm of the proton concentration. Observe the large variation of pH values. The local pH inside the core can rise to 9 in the tail regions, while the pH drops to values around 6.5 in the DNA regions. In conclusion, we see that the charging of a nucleosome is not ideal. The electrostatic potential, ion distribution, proton concentration, etc., are heterogeneous. In particular, we observe large pH variations. The charge of the nucleosome is strongly composition dependent. Note that this is not that this calculation are in absence of multivalent ions, which we will include soon. Currently, we are investigating larger chromosome arrays. Chromatin. 500,000 nucleus. How is chromatin structured and organized? The understanding of polymer physics is important to approach the problem of chromatin organization. However, chromatin does not behave as any of the standard models. Chromatin is a very special polymer and needs a different theoretical treatment. The self-returning extruded volume model is an extension we have a problem. Well, okay. The self-return executable model is an extension of the self-returning random walk model developed by us and published in 2020. The SRRW is no. De vuelta. Al revés. The self-returning executable model is an extension of the self-returning random walk model developed by us and published in 2020. The SRRW is a random walk with the possibility to return over itself. Each new step in the SRRW could be a return step or a forward step according to the probability distribution function. The distribution probability distribution functions depends on one parameter, alpha. The SRRW has two properties. It has no exuded volume and it is not a linear chain. We remove these problems in the SR exuded volume model. The final SR exuded volume configurations consist of a linear polymer with clusters, but no with no overlaps. We use 3 different folding parameter alpha and 4 different global volume fraction phi. Then in total we have 12 simulation phases. We choose the units so that each piece represents a nucleus. Notice that phi is a parameter in the simulation. Locally, there are variation in the volume fraction as if the resulting configurations are not homogeneous. For more dense case, the model chromatin has the size of human chromosome 16. Here are examples of the SRRW and its corresponding SR volume configuration. Immediately, we can appreciate that the SR volume configuration is bulkier as a direct consequence of removing the overlaps. If we zoom into a small area, we can see the details of how the SRRW overlaps are removed and more these nucleosomes appears in the SR exuded volume configuration. Exuded volume states are very important and it is necessary to have a realistic representation of chromatin. It is very difficult to visualize chromatin in 3D. Using a coarse graining method is helpful. Here we wrap the model chromatin with image created with the alpha shape method. SRRW. SRRW and SR exuded volume are different. We will only look at the SR exuded volume. Looking at the entire structure of the mesh, we see that it is reminiscent of the interface between two bicontinuous spaces. SR exuded volume is consistent with chromatin as a non-crystalline condenser. The formation of the correlated structure of chromatin is the result of the two probability distribution functions and exuded volume that effectively captures the processes leading to the packing of chromatin. Here we look at two polymeric properties, the end-to-end distance and contact probability. They show a crossover between intra and inter-domain regimes. The 12 simulated conditions are plotted here, grouped by alpha. There is a small effect of alpha, but almost no effect of the volume fraction phi. For large genomic separations, the results reflect the spherical confinement. Here we compare the theoretical and experimental results correspond to chromosome 1 of cells HDP 116. The agreement is very good. Both results show that the contact probability decays with slope minus 1. On the right side, we see a slab cut from the SR extruded volume configuration shown before. We convert our SR extruded volume configuration with to the mesh free extrusion. We convert our SR extruded volume configuration to a stack of images, trying to reproduce the output of a chrome stem experiment. The presence of packing domains and how they vary over the 100 nanometers slab is clear from the movie. The SR extruded volume model is for a single chromosome, while the experimental experiment corresponds to the whole nucleus. There is very good agreement between the theory and the experimental results. Theory and experiment. One quantity that can be measured in the experiments is the chromatin volume concentration, or CBC. We follow the experimental procedure of the chromium analysis, and we include the experimental results. SR extruded volume results for 5 equals 0.2 are similar to the experiments. Experimental procedure. Here we show how the output from stem and experiments are treated in order to find how chromatin organizes and identifies packing domains. Starting from a stack of images, the domain centers are determined and a 2D plus mass integral is calculated. The domain radius is measured from the domain density profile, and the packing domain, the parameter, are measured from the mass. Here are the distribution of the radius of packing domains. Experimental pure experiments. From the conformations obtained with the XR extruded volume model, we first extract a slab that we represent with a stack of images. We follow a procedure very similar to the experimental one. Then we determine packing domains and their geometrical set. Once we have determined the packing domains, we can characterize them by their effective radius, which is defined as the minimum in the density profile, starting from the domain's center. Violin flows is a way of visualizing statistical data commonly used in biological studies. The shape of the flow represents the probability or frequency distribution. The mean value and standard deviation are displayed with black lines. Grouping the results by alpha, semicolon. We see that the distributions shift to larger radius as the overall volume fraction increases. The majority of the domains have radius between 50 and 100 nanometers approximately, but distribution is highly skewed towards larger radius. There's very good agreement between the theory and the experimental results. Yes. It's a review experiment. The overall dependency on alpha and phi is better visualized from the plot of the mean value as a distribution of the global volume fraction as in this plot. Another structural property that captures the balance of low and high density regions is the hacking parameter. A summary of the results in this plot shows that P increases when phi increases, but and when the volume parameter alpha decreases. These results apply to the overall behavior of the ensembles of configurations characterized by alpha and phi. Calculating the individual D for each formation, we can represent the distribution of these values over the 12 different ensembles. The mean value of the distribution increase with increasing volume fraction and have a small dependency on alpha. It's small. There is very good agreement between the experimental findings and the theory. Now we will forget the global value of phi and use the local calculated value phi I and its corresponding the results of plotting these two local values against each other is shown in the left figure. Each color represents an alpha phi combination. Even though there is dispersion on the curve, this figure should suggest that the local density phi r is a major factor determining the value of the local. In conclusion, SR excluded volume is based on statistical return rules with no physical interaction except the excluded volume and chain coexist. However, SR excluded volume produce chromatin configurations that reproduce experimentally non-physical properties. SR excluded volume depends only on two parameters, alpha and phi. It is an efficient computational method. The wrapping mesh is reminiscent of the interface between two pi-continuous spaces. Each conformation is segregated in two specific regions, one which is in chromatin intensity and the second almost depleted of chromatin. We will trace the SR excluded volume configurations with the actual DNA sequence and architectural properties. We aim to reproduce high-C experiments involving millions of configurations. We will study diffusion of free crowders, proteins, transcription factor, etc. individual configurations. We will link the SR excluded volume method to create configurations with the molecular field to assess the distribution of ions and electrostatic potential. Muchas gracias.
¿Son preguntas? En este último caso, donde estás viendo si entiendo bien una única cadena, pero no, es mucho interesado, pero es una única cadena. Eso también, pero es un promedio estadístico sobre muchas cadenas.
Sí, sí.
Pero el objeto, los enlaces es una única cadena.
Sí.
En el núcleo vos tenés muchas cadenas.
Sí.
Entonces mi pregunta es, porque son objetos casi compactos.
Sí.
¿Hasta qué grado puede haber interpolaciones entre estos objetos?
Only.
No se puede con este modelo.
Sí, puede ser. Óptica.
Sí.
Núcleo. Arroz y arroz. chromatin 1.
Después comparaste tus modelos con imágenes de transmisión electrónica, ¿no? Pero no hay tampoco datos de fluorescencia de super resolución.
Sí.
Porque eso también fue, el TEM está como en una condición muy diferente, porque es más masivo, y por ahí eso, en cambio la otra puede ser como más comparable, si tenemos que considerar ese dato.
Pero tiene fluorescencia.
Interfiere en el
No, todos. Era bárbaro.
perdón, pensé que dijiste que el marcaje fluorescente altera todo y ya no es comparable. ¿Es esa la...?
Experimenta, fíjate.
Vamos a hacer la parte de eso.
No, estos nunca forman los brillos cristalinos.
Resulta que biological paper. Problem. Una cosa cromática es la quotation mark es no experimental, es experimental un paper, solamente un paper está. Y
Resultados.
es difícil, por ejemplo, este proteína es fácil, pero esto es slow. Y yo no se puede consenso. one paper.
Bueno, más que una pregunta es un comentario, siguiendo un poco la pregunta de José. José Córdoba, un método experimental para poder confirmar una estructura continua, sobre todo cuando hay agua, en las aguas, son las técnicas electrónicas, neutrones de bajo ángulo. Digo porque eso es una técnica que, por suerte, va a estar accesible dentro del par de años, ¿no? Pero hay otros lugares donde se puede hacer. Esto es tomografía de TEM.
Sí.
Cuando daría una información complementaria,
Claro.
me puede dar una idea de la distancia que hay, la distancia típica entre las dos casas.
Pero es pero es bárbaro, pero no vivo. Esto es no vivo. No, no vivo, es bárbaro. Dos nanómetros es veloz, pero es muy difícil, pero vivo Adin Bachmann hace IWS. Fluctuation 20 nanometers. Es espectacular. Es fascinante. In vivo. Pero es perdóname.
Sí. No, ya tengo la técnica, la ADN es una técnica óptica que permite observar fluctuaciones de densidad de nuestros sistemas, pero lo hace es simple y elegante.
Proteínas, todo, maravilloso. Pero Sí.
Pero yo no sé.
Sí, pero sí.
Bien.
No.
¿Cómo hacen para...? Ah, son estas. Por eso no como grado. Claro, hace el tiempo que quieran. Ah, breve, sí. Piensa que vale. Después devuelve un no, pero si les que devuelve ahora puedes solucionarlo. Sí. Yo también, pero esto es una posibilidad para adelante y una para atrás que son distintas. Pero no, nada más. Pero digo, si bueno, no para. No, nada. Que depende de. Sí, es que el igual en el principio que es la evaluación de esto y así. Es lo que se Esa es la posibilidad de pero ya depende de qué sucede.
Sí, sí, no.
Y bueno, este programa
La posibilidad de que vuelva una vez, la posibilidad de veces
Vamos tomando las cosas a medida que
esta mañana.
puro de pago. Gracias, la pasamos lindo. Con ustedes y con todo el mundo. Estamos mal bien, estar acá a usted. Iremos viendo también todas las cosas de salud. No hacemos tenemos que viendo porque cada vez que hacemos plan, después lo tengo que cambiar.
Estaban empadronados.
Poco a poco. Genial. Gracias, vuelta por la otra noche. Se cuida.
Están transmitiendo en vivo todavía. Fue grabado. Y bueno, me venía a despedir.
Se le